Good afternoon. My name is Paul Slorich, and I am the Business Development Director for ECOG. It's great to be here presenting at the Marine Autonomy and Technology Showcase, albeit in this pre-recorded format. But thank you to the team at the NOC and to everyone, of course, for tuning in. ECOG are a technology developer based in Aberdeen. Our main technology focus areas are subsea energy storage systems, typically battery storage, and remote power integration for offshore and subsea assets. Our goal is to enable sectors of the blue economy, all sectors of the blue economy, to be able to operate with fully clean systems so that existing and emergency ocean sectors can use our resources sustainably. Today, I'm going to introduce the Autonomous Offshore Power System, or AOPS for short, as a means of lowering the total cost of ownership of subsea systems by providing new, robust capabilities for operation, inspection, repair and maintenance of assets in the marine environment. I'll start with a brief introduction to ECOG and our HALO battery storage technology before moving on to cover the AOPS, the AOPS concept, for which we are providing a HALO subsea battery system to our US-based partner for an offshore test program commencing in Q1 2021. For those not familiar with ECOG, we were founded in 2013 with the intention of developing clean power systems for operating subsea hydrocarbon production assets using marine renewable energy technologies. The majority of our team come from a subsea engineering background in the oil and gas industries. Our current team is around 30 people operating across multiple disciplines. We're based at two sites in Aberdeen, our Davidson House headquarters and a nearby manufacturing facility where we do the bulk of our R&D work and, of course, our battery manufacturing. I guess more specifically, the company was created to develop products which address the energy transition and power problems at existing subsea assets. Now, we're almost solely focused on battery products and remote clean power generation systems for offshore and subsea assets. And the key themes that we look to address with our technologies are electrification and the sustainable power systems for offshore systems. For example, this could be life extension of brownfield hydrocarbon production systems using marine renewable energy technologies. We have one eye on the future with full electrification of subsea assets, including brownfield, field extensions, new tiebacks and new developments. And increasingly so, we're looking at remote power systems, including residential subsea vehicles, sensor packages, environmental monitoring and methane detection. And it's really this area, I think, that will be the focus of our autonomous offshore power system technology. But really all of these areas could be for, offshore hydrocarbon industry, it could be for offshore wind, CCUS, oceanography, defence, aquaculture applications, and basically most parts of the blue economy. Our core product is HALO, which is a modular scalable battery architecture, which we offer for really all of the previously mentioned applications. And we see this as one of the basic building blocks of the autonomous offshore power system concept. What is an AOPS? I guess one of the biggest challenges for sustainable long-term ocean operations is the availability of power. The concept of the autonomous offshore power system is to combine the benefits of wave power with seabed-based battery storage to deliver a new class of offshore power system. This is one which will provide power generation, energy storage, data transmission, communication capabilities, and continuous support of unmanned offshore equipment, vehicles, and sensor packages. ECOG have been working with Seapower, a US-based wave energy company, who are developing the AOPS solution under a US Department of Energy and US Navy-funded program. The program is being run by Seapower, but all the project partners will demonstrate the AOPS concept far beyond what has previously been trialled for any similar autonomous systems, with a 6-month trial scheduled for the wave energy test site offshore Hawaii commencing in Q1 2021. It's hoped that this will demonstrate the AOPS as a means of providing reliable, robust and regenerative power to subsea assets, which can be used as an enabling technology for a whole host of new applications across the whole blue economy. The image on this slide shows the basic AOPS platform concept. Basically, the AOPS will consist of Seapower's Sea-Ray wave energy converter, coupled with ECOG's HALO subsea battery technology on the seabed. What we are trying to demonstrate is a combined system that will provide reliable power and support systems to remote offshore locations. This is to reduce shore and vessel dependency, to replace carbon with renewables, improve human and environmental safety, and enable innovative, autonomous and digital capabilities. The system will be installed at the test site for a period of around 6 months initially, from wave energy, which will then be used to recharge the subsea battery system on the seabed. The subsea battery will be used to run a number of payloads to validate the usefulness of the platform for a range of applications. This will mainly be some external sensor packages, but importantly, we'll be operating and recharging an AUV on the seabed using remote over-the-horizon communications. In this initial trial, this will be a Saab Sabertooth platform, but could equally be another variant of subsea residential vehicle for future applications. So a bit more detail on the technology. This is a rather crude image, but hopefully displays the basic AOPS concept simply enough. The C-ray wave energy converter, or WEC, we will be using is a relatively small device with a fairly modest annual average output of 1 kilowatt. This will be coupled to ECOG's HALO system on the seabed using an innovative umbilical system, meaning that the HALO will form what we call the seafloor garage, which is essentially the WEC mooring. The battery system will initially have an installed capacity of 100 kilowatt hours in a structure weighing somewhere in the region of 6.5 metric tons. These technologies were developed by ECOG and Seapower wholly independently, but it's recognized by all the project partners that there's significant economic and technical benefit to be gained by coupling them into the AOPS system. In fact, this was always one of the main drivers behind the development of ECOG's HALO battery system. It's important, I think, to remember the intermittency of the wave resource is countered by an intermittent demand for this type of system. The AOPS will run some continuous loads based within the sensor packages, but the larger demands, the peak demands of the system will come from the periodic recharging requirements of any residential subsea vehicle. And this is precisely the benefit of coupling subsea battery storage with the wave machine. You can store the power when it's needed, such that it's always available on demand when it is needed. Importantly, both technologies are easily scalable, but the sweet spot at this stage is definitely a system which is capable of being packaged inside 1 or 2 standard shipping containers. The Seapower C-ray WEC is a hinged raft design with fore and aft generators and a heave plate for stability. It's got a small internal battery within the WEC, which provides power for the onboard hotel loads. The WEC's energy is fed to the subsea payloads via the HALO battery storage on the seabed. Essentially, that means the HALO acts as a buffer or a subsea accumulator, allowing the AOPS to maintain stable output for the payloads. The HALO has 2 battery packs. Each includes multiple battery modules, totaling approximately 50 kilowatt hours in each. And our HALO battery system uses lithium-ion chemistry, selected mainly due to superior energy density. The cell types we use are generally not pressure tolerant, so the AOPS design, we house our batteries in 1 atmosphere housing purged with dry nitrogen. ECOG's Central Intelligent Energy Management System is really the clever bit for the subsea system, which actively manages all power in and out of the HALO battery storage and provides battery management and safety functionality. This is all mounted on a single seabed skid with output connectors to the payloads. In this initial demonstration, the payloads will be located some meters away on the seafloor, from the seafloor garage, but equally these could be integrated into a single structure. I think it would be particularly beneficial to integrate the charging point for the AUV into the seafloor garage using an inductive charging method, and that's something that ECOG are particularly keen to incorporate into future product developments. As mentioned previously, the total weight of this seabed structure is around 6.5 metric tons, meaning that the whole system is easy to transport and easy to install from a relatively low specification vessel. The image to the right of this slide shows the basic building blocks of our subsea system: 2 battery packs and a centralized energy management system on a single skid. Please do excuse the cable management in this image. This was a dry build of a test system only. The final configuration of the HALO battery seafloor garage for the AOPS is shown in the lower left-hand image. complete with the dropped object protection structure, and the umbilical interface there is shown as well. So as I mentioned earlier, the AOPS will be tested initially at the Wave Energy Test Site offshore Hawaii. This is a US Navy site, which provides an excellent proving ground for offshore technology. The water depth at the test site is admittedly quite shallow, around 80 meters, but presents a good starting point for demonstrations, particularly for North Sea operations. The real importance of the test program is to fully understand the behavioral characteristics of the discrete WEC and battery storage technologies, which can only really be accurately demonstrated in the harsh marine environment. The overall capacity of the system in terms of kilowatts is a function of the wave machine size and the installed energy capacity in the HALO seabed battery. Excuse me. ECOG have run a number of case studies using 35-year data for the wave site and the output power from the WEC for the given conditions to create a prediction tool which shows the available power from the AOPS system. And this will be validated during the test program. The graphs on this slide are not particularly clear, but they provide a snapshot of the battery state of charge at any given period in time over a 365-day period. And this is a function of power in from the WEC, which is weather dependent, and output power to the payloads. What we know is that when the WEC is able to generate a stable power at decent level over time, the HALO's battery capacity of around 100 kilowatt hours is sufficient to provide long-term stable output to the required payloads. When the WEC's power input is not ideally sufficient or stable, the HALO is able to operate a stable output only for a limited time. And this time period will likely equate to about 1 month, 1 month's operation of the payloads, but could easily be increased by installing further battery capacity. During the trial, we will run the external sensor packages continuously, communicating the gathered data back to the HALO seafloor garage. And similarly, we will run a number of mission profiles with the AUV, demonstrating that the vehicle can autonomously recharge from the HALO energy source. We'll also have two-way data communication between the seafloor garage and the AUV. The HALO seafloor garage has multiple data points. All this data, together with the sensor package data and the AUV mission data, will be communicated back to the WEC, which provides a surface gateway for data recovery to the beach. In our case, in the case of our HALO, our Hawaii trial, this communication system will be managed by RigNet. So the next couple of slides will give some images of our HALO system, which is currently in manufacture. Some of these components that you see in these pictures will be installed subsea as part of the AOPS trial next year. I was particularly keen to show some images of the wet build as well, and to provide a little more information on the technical characteristics of Sea Power's system. But unfortunately, we have some restrictions on what we can publicize in that respect, and those restrictions were only being released at the beginning of this week. This is mainly due to the US government involvement in the project and their confidentiality requirements. I guess there's been some things happening over in the US which meant that this project perhaps wasn't the government's top priority recently. Hopefully by the time this recording goes out, there will be more publicly available information that I could share with anyone interested. However, starting from the bottom right, we have some images of the battery modules that will form the basic building block of the seafloor garage. Above that, on the right-hand side, are the housings, which are used to maintain a dry atmosphere for the battery systems and to house ECOG's Intelligent Energy Management Gateway. The top middle image there is one of these housings undergoing hyperbaric testing to simulate a depth of 1,500 meters. This test was done at the Balmoral Subsea Test Centre here in Aberdeen, which is a fantastic facility if you've never visited. Right over in the top left is one of the bulkhead flanges of the battery housings. This flange has some important safety features that prevent excess pressure or gas buildup in the unlikely event of a failure within the battery housing. We have some basic PRVs for pressure equalization, but the flange does also allow fast release of pressure through a far larger orifice. Bottom left is a very simple seabed skid that we will build this system onto. And to the right of that is an image of the pulse arc welding process that ECOG use on our battery cells. This is a very high quality procedure which ensures we build robust and reliable battery modules capable of operating for long periods of time in the subsea environment. This next slide is a bench test of our battery module internals. On the bench here, you can see around 50 kilowatt hours of energy separated across a number of discrete battery modules. This module train will be slid into the battery housing shown in the earlier slides. At the front of this image is some of the charge system, which will push power from the WEC into the battery modules. This will also be housed with the battery modules inside the housings, which will take power from the WEC via the Intelligent Energy Management System, which is ultimately responsible for battery management and distribution of the available power between all battery modules in the system. This image was taken a number of months ago at our R&D lab here in Aberdeen, and these batteries here have since been successfully subjected to UN 38.3 testing for transportation. To start wrapping things up, to conclude, ECOG are working with Seapower, a US-based wave developer who are developing the AOPS concept for regenerative clean power delivery to subsea assets. An initial 6-month trial will commence in Q1 2021, which will demonstrate the suitability, economic and technical benefits of the AOPS for powering oceanographic equipment and residential subsea vehicles. The two technologies, ECOG's subsea battery systems and Seapower's Sea-Ray wave energy device, were developed wholly, and partners have recognized the advantage had by taking a systems approach to development and demonstration. And all the project partners are keen to explore alternative applications for this technology, and we're always keen to hear feedback. Well, I'd just like to finish by thanking the NOC for the opportunity to present today, and thanks to everyone for taking the time to listen. I will reshare this last slide here, which has all my contact details. And of course, I'll be in the live Q&A coming up later this afternoon. Thank you again for your time.